Hi everyone. So let's see this question. In this question, what the question is saying. So we have this. Our language is this. Our first of all, our alphabet is this. Our alphabet is A, comma B, comma this symbol. Okay, this symbol. This is some symbol. I don't know what is this symbol, but this is some symbol. Question mark symbol. Okay, and our language is what? Our language is those strings. Basically, our language is like this. W, then this symbol, then W. This is our language. Okay. And basically W should be equal to W, and you can notice in the middle you have this symbol, and here W is a string of A, comma B. So what this means, can anyone tell me? Remember, our alphabet is this. In our alphabet we have these symbols. So in alphabet we have these symbols, but W is a string of A, comma B. W is a string of A, comma B. So it is like this. So this type of strings we have in this L. In this L we have this type of strings. Correct? Yes or no? This type of strings we have in this L. Okay, so this type of strings we have in L, right? Now you understood this language. So now you tell me one thing. You tell me one thing. For if you want to recognize this language, then can you find the middle? Now can finite automata find the middle? Now can you find the middle? Of course, now you can very easily find the middle, because you know that this will be the middle. So you are walking. The finite automata is walking. You are walking. Okay, you are walking. So when you see this, then it will tell you that this is the middle. So finding middle is not a problem. Correct? Finding middle is not a problem. This symbol tells you that this is the middle. So finding middle is not a problem. But still there is a problem. What is that? Finding middle is not a problem, but still there is a problem. What is that? First of all, there are two problems here. What are the two problems? The first problem is that you have to count this length. First of all, you have to remember this length, yes or no? Because this must be middle. This symbol must be middle. This symbol must be middle. So you have to remember this length. You have to remember this length so that you can confirm, you can verify, okay, that this is middle. And also you need to remember this W. So, okay, these two things, basically you need to remember this W. You need to remember this W also, and this length also. And this length also. But if you remember this W, then automatically this is redundant. This is redundant, yes or no? Because you are remembering W. So this is redundant. Can I say? Because you are already remembering W, to match with this. Okay, you are already remembering W to match with this. So this is actually redundant, I can say. So you don't need to remember length, basically, but you need to remember W. This is what you need to remember. You need to remember W. And how many possibilities? How many possibilities? This W can be what? This W can be what? So there are infinite possibilities. Okay, so I can say there are infinite possibilities. A power 2, A power 3. There are infinite possibilities. So this W can be anything. This W, we need to remember this W. And there are infinite possibilities. This W can be anything. So that's it. Very simple. So finally, this is your non-regular. So I can say this language is non-regular. Infinite possibilities. So it means L is non-regular. Now, can you give me the distinguishable set? Infinite distinguishable set, can you give me? Infinite distinguishable set. So what is the infinite distinguishable set? Tell me. Which set will work as infinite distinguishable set? Which set? This A power n you can give me very easily. A power n. This set will work as infinite distinguishable set. If you have any two A's, like for example, let's assume n is not equal to m. This is your A power n. This is your A power m. Then tell me such that this belongs to L, this does not belong to L. Give me extension. Can you give me extension? Of course, very easily you can give me this extension. You can give me this extension, right? This extension you can give. Correct or not? Is this clear to everyone? Okay, so very simple. So this set will work. Now I can say, now can you notice one thing? One interesting thing you notice. Do you remember this? I told you in the first class. Do you remember this? I told you in the first class. Yuvraj is saying any set will work. Tell me, can I say every infinite set is, can I say every infinite set will work? Is every infinite set is distinguishing set? Can I say this? Every infinite set is distinguishing set? The answer is no. The answer is no. For example, look at this set. Look at this set where you have these two symbols you have. Look at this set, a power n, b power n, a power n. So this set, you have 2 times. So ultimately, this is your, all are equivalent, pairwise equivalent. These are pairwise equivalent. These are pairwise equivalent. Okay, correct? So like this. So these are actually pairwise equivalent. So you cannot create any random set, but you can create this set. Very easily you can create this set. In this set, every 2 elements are distinguishable. Every 2 strings are distinguishable. Do you remember in the first class what I told you? In the first class, I told you that accepting a language, why we accept a language? What is interesting about this language? What they will do? In this in this TOC, in theory of computation, why are we accepting languages? What is interesting about these languages? Yes or no? These languages are boring. Okay, these languages, what they will do for us? So you can notice I told you that accepting a language is basically same as solving a yes-no problem. Accepting a language is same as solving a yes-no problem. This we have already seen. Okay, now you tell me, for example, this language, which problem this will solve? This language, which problem this will solve? Look at this language and you tell me which real life problem this will solve, which computational problem, this problem, which it will solve, which computational problem? Tell me which computational problem can be solved by this language? Which computational problem can be solved by this language? Yes, basically string matching. I can say basically you have 2 strings. Are they exactly same? 2 strings or text. Okay, 2 strings or text. Okay, over a comma b of a comma b. 2 string or text over a comma b. Okay, you have 2 strings. Let's assume you have 2 strings x comma y. Okay, over a comma b. Is x equal to y? Is x equal to y? Yes or no? This is the question. Basically, are they same? Pattern matching. So this computational problem, not pattern matching, this is actually string matching. This is actually string matching. I can say this is string matching. So what you will do, tell me? If you want to solve this problem, this is your computational problem, then what you will do? If I give you 2 strings x comma y, okay, if I give you 2 strings x comma y, which are on a comma b whole star, these are over a comma b whole star, given 2 strings x comma y. Okay, how to check is x equal to y? So what you will do? Tell me what your algorithm will be. What you will do? Tell me. Basically, what your method will be, I can say. What is your idea? Idea is very simple. What you will do? These 2 strings, you will just find, just check. Okay, just check this. Check if this belongs to L. Check that this belongs to L or not. Correct? Yes or no? Just check whether this belongs to L or not. This is what you need to check. Agree or not? This is what you need to check. Just check that does it belong to L or not. If it belongs to L, what it means? If it belongs to L, what it means? Remember x comma y, these are on a comma b whole star. If it belongs to L, it means x is equal to y. And if x is equal to y, then this will happen. And if this does not belong to L, if this does not belong to L, then x is not equal to y. So you can notice this language is solving a problem. Do you remember? Accepting a language is basically solving a problem. Correct? If some machine is accepting this language, let's assume some machine is accepting this language. Assume machine M. I don't know which machine M. This Turing machine. This can be Turing machine. So assume machine M accepts L. Then what can I say? Accepts L. Then what I can say? Then I can say machine M is solving this problem. Solves machine M will solve string matching problem. Correct or not? Solves string matching problem. Agree or not? So if machine is accepting L, then this machine is solving this problem, because what you can do for any two strings, given two strings x comma y on a comma b whole star, these are two strings on a comma b whole star, then what you will do? To this machine you will give this input you will give to the machine, and if the machine says yes, that it means x equal to y, and if machine says no, then x is not equal to y. Correct or not? Tell me, did you understand this? So accepting language is same as solving problem. You are solving real life problems, computational problems you are solving. Okay, let's move on. So this is the idea. And this language of balanced parenthesis. What are balanced parentheses? Language of balanced parenthesis. Let's assume this is parenthesis, open parenthesis, and let's assume this is closed parenthesis. Then what is the language of balanced parenthesis? The language of balanced parenthesis. So tell me, will this string in the language? Will this string be in the language? Just tell me, is this balanced parenthesis? Is this balanced? No, this is not balanced. Is this balanced? Is this balanced? Is this balanced? No, this is also not balanced. Is this balanced? This is also not balanced. So how will you write the statement for this language? How will you write the statement? Language of balanced parenthesis. First of all, what will be your statement? Balanced parenthesis. My question is, how will you write this as a statement, as a set builder? In set builder, how will you write this? Balanced parenthesis. I can say W belongs to alphabet is this. Yes or no? Agree? Alphabet is this. Open parenthesis, close parenthesis. Alphabet is this. What should I write? Can I say number of open parentheses is equal to number of close parentheses? Is this correct? Okay, is this enough? Is this enough? Can I say number of open parentheses is equal to number of close parentheses? Is this enough? No. So this is wrong. Why this is wrong? What is the reason? For example, this should not belong to L. This should not belong to L. This should not belong to L. Correct? This should not belong to L. This should not belong to L. But this is belonging. Here you have number of open parentheses is equal to number of close parentheses. So this is not correct. So what is correct? Tell me. Can anyone tell me? How can I write? Like number balance parenthesis. How will you define balance parenthesis? How can you define balance parenthesis? This balance parenthesis, how can you define? Tell me, what do you think? Okay, just tell me this point. Just tell me this point. Starting, okay, I should start with what? Just tell me this point. This balanced parenthesis, I should start with what? This balanced parenthesis, I should start with what? Just look at this balanced parenthesis. I should start with what? I should definitely start with open parenthesis. I should definitely start with open parenthesis. Okay. Now, see, very simple point what I'm saying. You can notice that you have to start with open parenthesis. So can I say that in every prefix of length 1, you must have open parenthesis? Can I say every prefix of length 1, every prefix of length 1 should be open parenthesis? Every prefix of length 1 should be open parenthesis. You can also notice that this is balanced parenthesis. In this, you can notice that in every prefix, number of open parentheses should be more than number of closed parentheses. Can I say? Can I say in every prefix, whatever prefix you take, in every prefix, what should happen? In every prefix, tell me what should happen. In every prefix, what should happen? Number of open parentheses must be equal to number of open parentheses. Number of open parentheses must be greater than equal to number of closed parentheses. Can it happen? Can it happen that in some prefix, can it happen like this? Like this, can it happen? In some prefix, number of closed parentheses can be here in this prefix, look at this prefix. Look at this prefix. Number of open parentheses is equal to 3. Okay, sorry. Look at this parenthesis. So yeah, this will not work. So which prefix we should check? So we should check, look at this prefix. Okay, look at this prefix. Actually, look at this prefix. This is also a prefix, correct? This is also a prefix. In this prefix, number of open parentheses, what is that? Number of open parentheses is 3. Number of closed parentheses is equal to 4. So that is the reason this is not correct. Yes or no? So do you agree? So I can say that, how can I write? I can write that basically in every prefix, this is how you can define. In every prefix, what should happen? In every prefix, number of open parentheses must be greater than equal to number of closed parentheses. Is this enough? Is this enough? Again, tell me, is this enough? What is the counter example? This is also not correct. This is also not correct. What is the counter example? Counter example is this. This is the counter example. This is the counter example. Okay, so tell me, what should I do? And number of open parentheses must, and in the string, and in W, number of open parentheses must be equal to number of closed parentheses. Now this is correct. Yes or no? Now this is correct. In every prefix, this should happen. In every prefix, this should happen. And in every W, this should happen. This is the definition of balanced parenthesis. Is this language regular? This balanced parenthesis language, is this regular? Is it regular? This is non-regular, right? Why this is non-regular? Because at any point of time, first of all, remember this condition. Look at this condition. Look at this condition. Number of open parentheses must be equal to number of closed parentheses. First of all, this should happen. Okay, in the entire string, number of open parentheses must be equal to number of closed parentheses. And also in every prefix, this should happen. So basically at any point of time, tell me what you need to remember. Because you have to check for every prefix. So at any point of time, you have to remember how many open parentheses, how many closed parentheses. At any point of time, you have to remember how many open parentheses, how many closed parentheses. Yes or no? Is this clear to everyone? Okay. So actually, now let me give you the infinite distinguishable set. Can you give me infinite distinguishable set? For this language, can you give me infinite distinguishable set? Let's assume this is A, and let's assume close parenthesis is B. So what set will work? Infinite distinguishable set. Will this set work? A power n greater than equal to 1. Will this set work? Tell me. Will this set work? Can I say this set will work? Can I say A power, for example, if I have maybe this set will work, right? Because this is, I can say open bracket power m, and this is open bracket power n. Okay. Then which string will distinguish them? Tell me, which string will distinguish them? Which string is going to distinguish them? So I can say this power n, this close parenthesis power n, this will distinguish them. So can I say this is infinite distinguishable set? Yes or no? We have infinite distinguishable set. Agree or not? So for this language, you can notice this is your language balance parenthesis. For this language, this set, look at this set. This set will work. This is your infinite distinguishable set. Infinite distinguishable set. So what I can say, this language is a non-regular. Very easy, right? This formal method is more easy, much more easy, much more intuitive. Okay, it gives you much more knowledge. So this is the idea. Okay, so let's see. Let's move on now. Okay, now tell me HTML. Can I say HTML is regular language? This is my question. C language is regular language. C language is not regular. Prove it. C language is not regular. Prove. Prove it. C language is not regular. How will you prove it? The C language. First of all, what is the alphabet? First of all, what is the alphabet? First of all, what is the alphabet of C language? What is the alphabet of C language? That is your ASCII characters. Your ASCII characters. That is your alphabet for the C language. For the C language, this is your alphabet. ASCII characters. ASCII characters. This is the alphabet. Okay. Now you can notice. And what is the language? What is the language? That is a valid C program. W is a valid C program. Is a valid C program. This is the language. W is a valid. Valid means syntax. Syntax must be correct. Syntax must be correct. No syntactical error. Okay, no compiler error. No compiler error. So you can notice. Now, how can I prove that C language is not regular? What I need to do? If you want a formal proof, give me formal proof. In interview, what you will say? In interview, which proof you will give? That proof I want. In interview, in some interview, if they ask you C language is not regular, prove it. Then what proof you will give? What proof you are going to give? Can I give infinite distinguishable set? If I give infinite distinguishable set, is that enough? If I give infinite distinguishable set, if I can give infinite distinguishable set, is that enough? Is that enough? That's enough, right? If I can give infinite set which is distinguishable, if I can give a set which is infinite and also distinguishable, then that is enough. Which set will work? You can notice this set will work. Look at this. This set will work. Okay, this set. N is greater than equal to 1. Will this set work or not? In C language, we have this. In C language, this should happen. In C language, what should happen? In C language, always this should happen. This should be balanced. Okay, this should be balanced. Yes or no? In C language, this should be balanced. Must be balanced. So, what I can do? Can I prove that this is infinite indistinguishable set? For the C language, your language is C language. Your language is C language. Now, for the C language, can I prove that this set, look at this set. Look at this set. Look at this set. This is your set. N is greater than equal to 1. Can I prove that this is infinite indistinguishable set? Sorry, infinite distinguishable set. This is an infinite distinguishable set. And you can very easily prove. What you will do? Okay, this is your, this power N, this power M. If M is not equal to N, then who will distinguish them? Okay, who is going to distinguish them? Who is going to distinguish them? So I can say some more things I have to give you. Of course, there should be man and something. So let's assume something is there. Man. Okay, man is there. Okay, let's assume this type of thing is there. Man. Because directly if you see, okay, please understand one thing. Please understand one thing. If I directly tell you, then actually they are equivalent. Yes or no? If your C program directly starts like this, can your C program start with this? Can your C program start with this? I think not. I think C program cannot start with this, right? I think C program cannot start with this. You can check it out. Okay, C program cannot start with this. C program can start with something like this, hashtag and something, or C program can start with maybe man. Okay, so C program cannot start with this. So here actually, okay, so what I need to do, something, let's assume some already there, something like initially, hashtag, okay, has include stdio.h, man, everything is there, let's assume. Okay, for a moment, let's assume. Okay, man, so let's assume there is man or something. So let's assume everything that is required, that is there. Everything that is required, that is there. Okay, just assume. So let's assume there is man here. Okay, let me assume there is man here. You are getting what I'm saying, right? Okay, so anyway, you don't have to worry about it. Let's assume whatever you need, that is already there. Whatever you need, that is already there. Let's assume. Now you can notice that now I can say that this power n, okay, this power n, this will distinguish. Now this belongs to C language and this does not belong to C language. So what we have proven? What we have proven? We have proven that this set, we have proven that this set is in infinite distinguishable set. Yes or no? Too much technical proof. Yes or no? Too much technical. A lot of technicality I have covered. But anyway, let me tell you, this proof will definitely impress any interview. In interview, if they ask you this type of question, then if you give this proof, it will definitely impress them. Because, okay, they will not be expecting this much, like, first of all, they will not be expecting, I can say, formal proof. And similarly, HTML, can I say HTML is regular? Can I say HTML is regular? HTML is also not regular, because in HTML, what we need, this type of, I can say, tags should match. Yes or no? In HTML, the tags must match. So HTML is also not regular. Can I give this question as a homework? Can I give this question as a homework? Okay, so take this question as a homework. Do something from your side, understand the language, and then you prove that this is non-regular. Okay, so this is what we need to do. Now let's see the formal statement of Myhill Nerode theorem quickly, because we have seen everything. We have seen the distinguishing strings, correct? Two strings are distinguishable. When can I say two strings are distinguishable? That we have already seen, correct? So two strings are distinguishable, that concept we have already seen. When can I say two strings are distinguishable? Now what Myhill Nerode theorem says? What Myhill Nerode theorem says? Now let's see the Myhill Nerode theorem. Now let's see this Myhill Nerode theorem. What is this Myhill Nerode theorem? This Myhill Nerode theorem is like this. First thing, tell me, let's assume given language L. Let's assume there is a given language L. This language can be any language, regular or non-regular. This is a given language L. Now tell me, if there exists an infinite distinguishable set, if there exists a infinite distinguishable set, tell me, if there exists an infinite distinguishable set, what that means? Infinite distinguishable set, what is the definition? Infinite distinguishable set, what is the definition of infinite distinguishable set? For any language, what is the definition infinite distinguishable set? So you can notice, if you have given language L, then what is the definition of infinite distinguishable set? I can say, first of all, this is an infinite set. Agree? I can say this is an infinite distinguishable set S. So I can say, first of all, S is infinite. First of all, S must be infinite. And what should happen? Tell me. And what should happen? It must be infinite, and every two strings are distinguishable. Yes or no? Every two strings in L. Every two strings. Okay, every two strings in S are distinguishable by L. Are distinguishable with respect to L. Correct or not? Yes or no? Agree or not? So this is your infinite distinguishable set. But this same statement, can I write technically? Can I write technically? This same statement I can say that for all W comma U, for all W comma U in sigma star, what should in S, sorry, for all W comma U in S, for every two string in this set S, what should happen? If they are different, for all W comma U, for all two strings, take any two string W comma U, take any two string W comma U, what should happen? For all there should exist a Y belonging to sigma star. There should exist a Y belonging to sigma star, correct? I can say whatever two string you take from this, so you can take any two string from this, there should exist a Y such that such that what will happen? Such that one of them will be final, one of them will belong to L. Okay, exactly one of them, exactly one of WY comma UY is in L. Exactly one of them is in L. Exactly one of them means one of them must be in L and another must be not in L. This is the definition of infinite distinguishable set. Do you agree or not? The definition is clear. Infinite distinguishable set. Now, what Myhill Nerode theorem says? This says that if you have some language, and for this language, if there exists some infinite distinguishable set, if there exists infinite distinguishable set, IDS in short, let's call it IDS. If there exists infinite distinguishable set, then what can you say? Then what can you say about L? If there exists some infinite distinguishable set, then L is non-regular. Then L is non-regular. And what is another statement? Similarly, if there is no infinite, tell me, if there is no infinite distinguishable set, if there is no infinite set in which you have pairwise distinguishable string, then what I can say? If there is no infinite distinguishable set, then L is regular. Then L is regular. That's it. Quite simple. Yes or no? So very simple. This Myhill Nerode theorem. This is the statement of Myhill Nerode theorem. So, for example, for this we have infinite distinguishable set. For this we have infinite distinguishable set. Okay, like this. This is the idea. I hope this idea is clear to everyone. Okay, so you can notice all the things. Now tell me about this one. Is this language regular or not? W ends with 10. W ends with 10. W belonging to 01 whole star, and W ends with 10. Is this language regular? Yes, this language is regular. But can you notice in this language, can you create infinite distinguishable set? In this language, can you create infinite distinguishable set? Can you create infinite distinguishable set? No. How many? Okay, what is the largest distinguishable set you can create? What is the largest distinguishable set you can create for L? With respect to L, I can say, what is the largest distinguishable set with respect to L? For this language, what is the largest you can create? Tell me. What is the largest you can create? Look at this. These 4 strings I am giving you, ending with 10. So let me give you these 4 strings. Are they distinguishable? Are they distinguishable? Look at these 4 strings. Are they distinguishable? Check. Are they distinguishable? Verify if they are distinguishable. If they are pairwise distinguishable. Verify if they are pairwise distinguishable. Are they distinguishable? Pairwise. Are they pairwise distinguishable? Yes, of course. Because these two are distinguishable by whom? These two are distinguishable by empty string. These two are distinguishable by empty string. So you can notice that. Okay, what about these two? So you can notice 10, anything. 10, anything. 10, anything. They are distinguishable by epsilon. I can say they are not equivalent. I can say they are not equivalent. This string and this string are not equivalent. By whom? Because of whom? By empty string. And what about this 0, 0 and 1, 1? They are also not. By whom? 0, 0 and 1, 1. They are distinguishable by whom? 0, 0, 1, 1. They are distinguishable by 0. Very good. Okay. 0, 0 and 1, 0, 0 and 0, 1. They are distinguishable by 0 again. 1 1 and 0 1. 1 1 and 0 1. What about them? 1 1 and 0 1. What about them? 1 1 and 0 1. 1 1 and 0 1. 1 1 and 0 1. What about 1 1 and 0 1? Tell me. What about 1 1 and 0 1? They are equivalent. They are equivalent, right? They are equivalent. 1 1 and 0 1, they are equivalent. You can check 1 1 and 0 1, they are equivalent, correct? Because you can clearly see, look at this. Your language is ending with 0 1. Your language is ending with 1 0. This is your language. Now you look at these two strings. Look at these two strings. Now, whether you are, okay, if you are ending with 1 0, okay, if you put, for example, let's assume this belongs to L. Then what it means? If this belongs to L, then what are the possibilities for Y? Then what Y can be? Either Y is 0 or Y is ending with 1 0. Either Y is 0 or Y is ending with 1 0. Either Y is 0 or Y is ending with 1 0. Yes or no? Correct or not? Either Y will be 1 0. See, if this Y is there, okay, if this belongs to L, then either Y will be 0 or Y will be ending with 1 0. Now for this type of Y, what can you say about this? For this type of Y, if you put here, this type of Y, if you put here, then this will also belong to L. Yes or no? Do you agree? Then this will also belong to L. If you put this type of Y here, so I can say they are equivalent, correct or not? These two are equivalent. So maximum, okay, what is the largest you can create? What is the largest set you can create? What is the largest set that you can create? What is that? The largest set you can create is, my original question was, what is the largest set that you can create? Largest distinguishable set that you can create. So the answer is what? Tell me. The answer is what? Size 3. Largest you can create size 3 set. Size 3. Largest set that you can create that will have size 3. So I can say that for this language, you can notice for this language, I can say the largest distinguishable set that you can create. The largest distinguishable set is of size 3. Yes or no? Is of size 3. The largest. For example, this set will work. Do you agree? This set will work. Like this set will also work. This set will also work. This set will also work, correct or not? This set is also distinguishable. These are also pairwise distinguishable. This set will also work. So I can say largest distinguishable set is of size 3. And now one very interesting thing. I hope you will find it very interesting. Now you make the DFA for this. So I am saying largest distinguishable set is of size 3. Now you make DFA for this, minimal DFA. How many states in minimal DFA for L? Number of states in minimal DFA for L. Number of states in minimal DFA for L. Ending with 1 0. It should end with 1 0. It should end with 1 0. If 0 is coming, I will go here and end with 1 0. If another 0 comes, then I will go here. If 1 comes, I will go here. And in this state, if 1 comes, no problem. How many states you got? How many states you got? So number of states is 3. Is this a coincidence? Is this a coincidence? This is not a coincidence, because remember, if you look at this language, then what this language will do, this language, if you look at ending with 1 0, for this language, the largest distinguishable set is of size 3. The largest set in which you have pairwise distinguishable, string, that has size 3, and minimal DFA, And minimal DFA also has size 3. Minimal DFA also has size 3. This is not a coincidence, because what this language does, what this language will do, this language will divide sigma star into 3 parts: equivalent strings, equivalent strings, equivalent strings. What this language will do, this language will divide all the strings. All this is the all strings. You can notice this is all strings. So what this language will do, this language will partition all the strings into 3 parts. One part will have ending with 10. One part is going to have, I can say, ending with 10. All these strings will be here. All these strings are equivalent, yes or no? Ending with 10, all these strings are equivalent, correct or not? All the strings which are ending with 10, they are equivalent. All the strings that are ending with 10, they are equivalent, correct? Yes or no? Tell me. And you can notice all these strings which are ending with 11 or which are ending with 01, they are also equivalent. You can notice this state. Look at this state 3. What this state is telling you? Look at this state 3. What this state is telling you? Which is this? This is ending with 10. This is ending with 10. And what is this 1? What is this 1? This is ending with 00. Yes or no? I can call it ending with 00. Can I call it ending with 00? This is ending with 00. And you can notice that this is ending with 01 or 11. And this is ending with 01 or 11. Ending with 01 or 11. Tell me, did you get it? So 3 categories will be created. All the strings which are ending with 00 will be here. All the strings which are ending with 10 here. All the strings which are ending with 11 or 01 here. And the remaining strings, is there any remaining string? All the strings are covered or not? Did I cover all the strings? Did I cover all the strings? No. No. Did I cover all the strings? No. Empty string will be here. Empty string will be here. 0 will be here. And 1 will be here. Now every string is covered. Now every string is covered. Ending with 01, these are here. Ending with 11 are here. Vani, ending with 01 is covered here. Ending with 01, that is covered here. Now every string is covered. Now tell me, now you can notice very simple that. So basically, with respect to this language, what this language will do, because of this language, this partition will happen. Because of this language, all the strings, this partition will happen. In this partition, look at this partition and tell me which should be the initial state in the minimal DFA. Look at this partition and tell me which should be the initial state. Initial state will be where you have empty string. Initial state means where you have empty string. Where you have empty string, that will be the initial state. And what will be the final state? What will be the final state? That will be your L. Your final state will be L. Final state will be L. So can you notice, because of this L has partitioned. This L has partitioned. What this L has done? L has partitioned sigma star into 3 equivalence, I can say equivalent sets. I can say 3 equivalence classes. 3 equivalence classes. Because within each class, every 2 people are equivalent. Yes or no? Every 2 people are equivalent. This and this, they are equivalent. This and this, they are equivalent. So I can say every 2 people are equivalent. So what this L has done? L has partitioned sigma star, all the strings, into 3 equivalence classes. Hence minimal DFA for L will have 3 states. Minimal DFA for L has 3 states. I hope this point is clear. Okay. Now, anyway, let's take a, this is enough. Now let's, okay, you can watch your match. Okay. But we will continue actually. Okay. So now you can watch your match, but small thing is remaining. Very small thing is remaining. Everything actually we have seen. Just I can say it's just a reading. We just have to read. Okay. But anyway, so we will continue. Tomorrow we will continue. Okay. So this actually very small thing is remaining, that is Myhill Nerode equivalence relation. We have seen Myhill Nerode theorem. This Myhill Nerode theorem we have seen, correct? So we have seen Myhill Nerode theorem, we have seen. This Myhill Nerode theorem we have seen. This theorem we have seen. Now one topic is there, that is Myhill Nerode equivalence relation. This topic is there, Myhill Nerode equivalence relation. This is a very small topic. This we will see in the next lecture. But this Myhill Nerode theorem we have already seen. This theorem we have already seen. What this theorem says? Do you remember what this theorem will tell you? This theorem says that for any language, if there exists infinite distinguishable set, then language is non-regular. And if there is no infinite distinguishable set, then language will be regular. So this is a two-way theorem. This is a two-way theorem, correct? If language is regular, I can say if L is regular, then what will happen? Then there will exist infinite distinguishable set. Okay. And you can notice if there exists infinite distinguishable set, then it will be regular. So this is two-way. This is two-way. And if L, non-regular. If L is regular, if L is non-regular, this will happen. If L is regular, then what will happen? No infinite distinguishable set. And if there is no infinite distinguishable set, then language will be regular. This is your Myhill Nerode theorem. Okay. Okay. Thank you, everyone. Anyone has any doubt in this? Please tell me. Any doubt? Any doubt in this topic? Let me know. Is there any doubt? Please tell me. Okay. So tomorrow, actually, what I will do, this Myhill Nerode equivalence relation, this I will record. Okay. Is that fine? Only very small topic, this Myhill Nerode equivalence relation, this I will record today. Tonight I will record. And tomorrow we will start the next chapter. The next module we will start. Context-free languages, context-free grammars, push-down automata. The next module, module number 2, we will start tomorrow. Everything we have seen. So if you have any doubt, please let me know. In the group, you can tell me. Okay, in the Telegram group, you can tell me if you have any doubt. Okay, pumping lemma, DFA, NFA, regular expression, this Myhill Nerode theorem. These are the topics we have seen. Okay. Okay, thank you, everyone. See you tomorrow. Yes, I will upload the notes. I will upload the notes now. Okay, thank you.